sklearn, cross-decomposition, PLSCanonical a deep dive. PLSCanonical, short for partial least squares canonical, is a powerful statistical method for dimensionality reduction and feature extraction in multivariate analysis. It's particularly useful when dealing with datasets having high dimensionality, correlated features, and a potential for multicollinearity. Let's dive into its details. 1. Principle of PLSCanonical. Goal: find linear combinations of features from two datasets X and Y that are maximally correlated with each other. Process it iteratively extracts latent variables LVs, which represent underlying relationships between the two datasets. These LVs are orthogonal to each other, meaning they capture distinct information. Key idea: the algorithm finds LVs that maximize the covariance between the corresponding projections of X and Y onto these LVs. This ensures that the extracted components are highly correlated with their counterparts in the other dataset. Relationship to other methods. Principal component analysis. PLSCanonical can be seen as a generalization of PCA that takes into account the relationship between two datasets, while PCA seeks to maximize variance in a single dataset. PLSCanonical aims to maximize the covariance between two datasets. Canonical correlation analysis. CCA. PLSCanonical shares similarities with CCA, but it incorporates a regularization step that helps deal with multicollinearity and noisy data. 2. Working mechanism. 1. Initialization. The algorithm starts with initial estimates for the latent variables. 2. Iteration. It iteratively refines the LVs by maximizing the covariance between the corresponding projections of X and Y. 3. Projection. At each iteration, the data is projected onto the current LVs, resulting in new scores for each dataset. 4. Weight estimation. The algorithm calculates weights for the original features to reconstruct the projected scores. 5. Convergence. The process continues until a convergence criterion is met, usually when the change in the covariance between the projections becomes sufficiently small. 3. Mathematical formulation. X input matrix for the first dataset N samples X, N features X. Y input matrix for the second dataset N samples X, N features Y. WX weights for the X features N features X, X N components. WY weights for the Y features N features Y, X N components. TX scores for the X dataset N samples X N components. TI scores for the Y dataset N samples X N components. N components. Number of latent variables to extract. The objective is to find WX and WY that maximize the covariance between TX and TI, subject to the constraint that the LVs are orthonormal. Maximize COV TX, TI, subject to WXT WXI, WYT WYI. 4. Applications in machine learning and data science. Predictive modeling. PLSCanonical can be used for predicting one variable from another, even when they are both high-dimensional and correlated. Feature extraction. It can extract meaningful features from complex datasets by identifying the most informative relationships between variables. Data integration. It helps integrate data from different sources by finding common underlying patterns. Multi-block analysis. PLSCanonical can be extended to handle more than two datasets, which is useful for analyzing complex systems with multiple interacting components. Bioinformatics. It finds application in areas like gene expression analysis, where it helps understand the relationships between different molecular profiles. Marketing and customer analytics. It can be used to analyze customer behavior. product preferences, and market trends. 5. Advantages of PLS-Canonical. Handles multicollinearity. PLS-Canonical is robust to multicollinearity, which is a common problem in high-dimensional datasets. Reduced dimensionality. It effectively reduces the dimensionality of the data while retaining important information. Improved interpretability. The extracted latent variables provide insights into the underlying relationships between datasets. Predictive accuracy. It often leads to better predictive accuracy compared to traditional methods, like linear regression. 6. Disadvantages of PLS-Canonical. Computational complexity. The algorithm can be computationally expensive for large datasets. Sensitivity to scaling. The results can be sensitive to the scaling of the input variables. Model selection. Choosing the optimal number of latent variables can be challenging. Assumptions. It assumes linearity and normality in the data, which might not always hold true. 7. Implementation in Python. sklearn. Python. From sklearn, cross-decomposition. Import PLS-Canonical. Create an instance of the model. PLS-Canonical components. 2. Fit the model to the data. PLS. Fit X, Y. Get the latent variables. TX. PLS. Transform X. Type PLS. Transform E. Predict Y based on X. Y. PRED. PLS. Predict X. 8. Important parameters. N components. Number of latent variables to extract. Scale. Whether to scale the input data before fitting. Algorithm used for the PLS fitting. Copy. Whether to copy the input data before fitting. 9. Key considerations. Data preparation. Ensure the data is appropriately scaled and preprocessed before fitting the model. Model selection. Carefully choose the number of latent variables to avoid overfitting or underfitting. Validation. Use cross-validation or other techniques to evaluate the model's performance. In conclusion, PLS-Canonical is a powerful and versatile tool for exploring relationships between datasets, reducing dimensionality, and extracting meaningful features. It's particularly beneficial when dealing with complex datasets with high dimensionality and potential for multicollinearity. However, it's essential to understand the underlying assumptions and limitations of the algorithm and use it judiciously in real-world applications.